nonlinear regression function. At first, why do we use the nonlinear form? Okay, so at first we use the textbook data set. It's about the school data in California. Okay, so it's named CS School, California School. Okay, this data set is for data file, so you should import the package foreign in R. You can download the data set onto your core. I also upload this data set. And you can copy my code in Beamer. You can change the path and to run this code, and you can get the same result. Okay, so you can get this result. Okay, so for the str and test score, you can find they are linear relationship, but for the income and test score, if you use the linear regression, you cannot fit well. So maybe we can consider the quadratic form or another high power form to fit this model. Okay, so this is quadratic form. Okay, so and then we should define the general form for a nonlinear regression. Okay, so in textbook, he say if the relation between y and x is nonlinear, the effect of y of the change in the x is depending on the value of x. You can write down this form. It's about if y is by definition, conditional expectation for this term is like maybe like a function of the x1. So maybe I use some example. So if the example for yi beta 0, beta 0, beta 1 times s1, beta 2, s1 I squared plus ui. And this example model have the result is about beta 1 plus 2 beta 2 x1. Okay, so you can get the form. The marginal effect is related to the s1. It's not a constant, so we should consider nonlinear regression model. And the nonlinear regression model, we consider the nonlinear form for the function of x, all regressors. In a linear regression, you consider the form is like this. Okay, so here we consider the nonlinear form. We use the function of all regressors x, s1 to sk. So we change this form to the general form. You can use the log, exponential, another you want. Okay, so and ui is error term, is the same. And here we should know the expected change and predicted change. In an expected change, he used the original model form. You cannot use the data. If you want to use the predicted change, you can plug in the data and the estimation result. So here you get a hat. Okay, so because you use the data set to estimate. And here is about some step for the model nonlinearity. The first step, choose the possible nonlinear relations, maybe log. polynomial, exponential, and so on. And second, estimated by OLS. Maybe sometimes you can use another estimation method, but in our class we also always use the OLS method. And third, you can see the coefficient is significant or not to decide whether you use the nonlinear model. So you should see the coefficient significance. And third and fourth is about partial nonlinear equations. So sometimes we use the programming software to do this step. Okay, so do it by hand is very hard. And fifth is about estimate the effect for the change. Okay, so in the first step, we talking about the polynomial nonlinear equations. Okay, so we use the different power in the model. We use the only xi in the model. Here is the xi squared. xi with the power r. Okay, so if r equal to 2, we call it a quadratic model. If r equal to 3 is a QB model. Okay, so you can use the estimation and inference for OLS directly in this form. You can see the x2, x squared as the different, as the new variable, maybe as x2, x1, x2, maybe x with the power r is xr. You can see at the new reversals. So you can do the test for the coefficient. And how can we determine the degree of the polynomial? At first, you should choose the maximum degree you want to use. Sometimes we use about 3 and 4. And then we do a t-test for the full model. So you should do the highest power to test the significance. Okay, so if you reject null hypothesis, you can stop. If you don't reject null hypothesis, do the next step. Reduce the power to 1. So if you discuss the r with the power r, if reject, stop. Not reject, do a power with the r minus 1. If you reject, stop. If you not reject, do the r minus 2 again, and so on, until you reject the null hypothesis. Okay, so in my notes, I use some different model. Here is about simple linear regression. Test score on the income. Sorry. Here is a simple linear regression. And model 2 is about quadratic form. And model 3 is a cubic model. Okay, so we use the high power, is about r equal to 3. So at first we should test the beta 3 in this model. So you can see here, it's not we not reject. So we should consider the power 2 square, income square. So here, we reject. So we stop. So we use the model 2. Okay, so that's all for the polynomial topic. And now we should talking about a log regression model. At first, we should talking about log difference. Okay, so how about this result? Log 1 plus h is approximate to h. Okay, so you should know the Taylor expansion in your calculus course. So we should define the some function of x is about log x. If we use the Taylor expansion at the x equal to 1, we can write down this result. Okay, so we can plug in each term and have a result. Log 1 plus h is approximate to h if the h is small. Okay, so we can use this result to get this. Log x plus the delta x minus log x. Okay, at first, because you should know the log operation, log a minus log b is equal to log a divided by b. Okay, so we can use this operation property to plug in this equation. And you can see this result. Okay, and then we can, here is 1. Here is delta x divided by x. Okay, so here we use this property in this page. Log 1 plus h is approximate to h. So h here is delta x divided by x. Okay, so I also use R to demo the true value and approximation value. You can see here, if x equal to 100, if delta x equal to 1, true value is about this. The approximate value is about this. Okay, so you should know this example is very important because we should talking about the next topic, linear log model. Okay, so how about linear log model? Linear log is mean y is linear and x is log. We use log form. So we call it a linear log model. And log linear is because y use the log form, x use the linear form. And log model is because y use log form, x use the log form. Okay, so linear log model. We should talking about a change to explain the coefficient. Okay, how about a delta y? Delta y is mean when x plus 2 plus delta x s grade up to or down to x plus delta x, y to change Okay, so here we can write down this equation. It's by delta definition. It's about change. We only change x to x plus delta x. And here is plugging x. Beta 0, beta null, and beta null we can reduce. And we only have a beta 1 times log x plus delta x divided and minus log x. And here we know this result. Okay, so this result about x delta x divided by x. Delta x divided by x here. Beta 1, beta 1. Okay, so we have this result. So if if x grade change for 1%, then y, how about y? You can see this example. If x change to 1%, then y change 0.01. So here, delta y is change 0.01 times beta 1. Okay, so this result is follow this example. So I think this example is very important to explain the linear log model coefficient. Okay, so you should memorize this result. And next is log linear model. You do it again for the change. And we do the different. We discuss the log delta y divided by y. Is approximate to this log y plus delta y minus log y. It is from this property. We change to the x to the y, and right hand side to the left hand side, and right hand side to the right hand side. So you can see this property. And next, we plug in the change into the model. Okay, so beta node, and beta 1x. So we only have the beta 1 times the delta x. So if x change 1 unit, the y is changed. Y is changed about 100 times beta 1%. Okay, so you can use a different direction for a linear log model. Here's 1%, 0.1, or is it equal to beta 1%? So %, and C is about if this is change 1%, and here is about beta 1. So you can see okay, so they are the same. You should know they are equivalent for this result. You only change the different directions. You only times the beta 1 to the right hand side. Okay, so you can know this. And next is a log model. Okay, so this coefficient is about elasticity. You can know this very clearly in your microeconomics. Okay, so I think if x changed for 1%, the y is changed beta 1%. Okay, so very clearly. Okay, so you can do the formula by R. run the fit model. In if you want to use a log, you use a log function, log common in R. You can directly use into the formula. I think it is very easy. So here you can see this model result, and you should do the practice to explain the coefficient meaning. So how about this? How about this? How about this? How about this? You should do the exercise. Explain the coefficients. Okay, so this page you should do the exercise. And next, we're talking about interaction between these two independent variables. In the type 1, we discuss interaction between the two binary variables. Binary variable is dummy variable. They are the same. Okay, so dummy. Sometimes we call the categorical variables. So different name, but they are different meaning. Okay, so here you can consider this form. This term is about interaction term. How can I explain this term? Okay, so other thing be equal, we assume the D2 is constant. How about the effect on Y if the change in X in D1? Okay, D1 is equal to 1 and 0. You can see the change. And D2 have the same value. You can plug into the list. Okay, so this term is about, I think, beta 0 plus beta 1. This term is about beta 0. Okay, so here we can do this form. We can have this result. So we can see the effect on Y of the change in D1 is depending on the D2. So I also run the equation 8.30 in R. In R, how to use the interaction term? You can use the times sign directly. In data, you should generate a new variable, but in R, you can directly use the interaction term, log term, square term, different power term in the model common. Okay, so next is about interaction between the continuous and binary variable. You can see the three types. Okay, so I think in class we discussed the type 2. Okay, so different types have different plots with different figure. Okay, so type 1 is about, you can see here, if di equal to 1, if di equal to 0, they are different. If di equal to 1, its line is upper line. If di equal to 0, its lower line. Okay, so they are changed to the intercept, but they have the same slope. And type 2 is about, maybe teacher don't discuss this term in the class, but maybe in your final exam. So you should focus on this topic, because in your midterm, the final questions, don't talking about in the lectures, but you can see this question in the midterm. Okay, so maybe this topic in your final exam, I don't know. So you should prepare to it. And if the d1 equal to 1, it's like di equal to 1, it's like this. If di equal to 0, it's a lower line. These two models have a different intercept and different slope. So you should know this result. And type 3, you only change the slope. So you have the same slope, same intercept. So here is the d1 equal to di equal to 1 and di equal to 0. So you can see this result. Sometimes we use the type 2 model to feed the data because sometimes we only use the type 1. It's about maybe 75% to 18%. Here's about maybe 10 to 15%. The type 3 is very smaller, up 5%, lower 5%. Okay, so most of you use the type 1, another is type 2. And you can run this example, equation 8.34 in your textbook. I get this result here. And type 3 is about interaction between the two continuous variables. Okay, so if you have a continuous property, you can use the partial derivative directly. Okay, so you can use this partial FOC. You can see is if the other thing be equal. So we respect to x1. So other thing be equal. They are equal. They are constant. They are constant. Okay, so we can see here. If we do this, we have this beta 1, beta 3, x2. So we have this result. So the effect on y of change s1 is depending on the x2. Okay, so in your textbook, he used the discrete form, but I use the continuous form. It's a general form because we use the two continuous variables. And here you can see this. You can see this result for the equation 8.37. So in the interaction term, you should know the coefficient. Maybe your effect is depending on specific variables. Okay, so you cannot explain the coefficient directly, but you can write down the form. Okay, so now we see the classwork in your lecture. Okay, so in your lecture we use the classwork 1 is about exercise 8.3. Okay, so this question is argued to some dummy variables. It defines the binary variables about small class, moderate class, large class. The threshold is about 20 and 25. Okay, so you can see this. If you have the three dummy variables, you have two choice. One is about you can use a two dummy variable with the intercept. The other is you also dummy variables, but without the intercept. Okay, so you can consider the part A is about sketch the argument. Okay, so the argument is about in a small class, they have the positive relation for the str and test score. For a large class, they are different way to the effect. So it's a positive and it's a negative. So you can write it down here. If this str test score maybe 20, 25. So how about here? I don't know because the question don't tell to me. But you can run this for the data set. Okay, how about part B? Part B is about we discuss if the one person try to estimate this regression, he used all dummy variables and the intercept. He say he cannot. He has some error. So how about this question? You have the dummy variable trap. So you have the two solutions here. UK minus 1, this means here is about 2 dummy variables with the intercept. Any other U3 dummy variables without the intercept. You have at least two solutions. Okay, so I also do this by the code. Okay. How about, and next is exercise 8.6. Part A is about, okay, so I see. This part 1 is about describe a nonlinear relation. Okay, so the researchers argue to person of this, I think this is about percent of the English learner. For this, have a little effect. And for this, have a large effect. So you can create a dummy variable to evaluate this result, evaluate this effect. Sometimes you can, I give you some very more binary variables because I'm not sure whether this researcher has argued different questions and other questions. So I also create all dummy variables for this person of the English learner. Here's 1, 2, 3, 4. But because we also use a model with the intercept, so we cannot use all dummy variables. So here is we don't define the binary variables. We can consider this form to evaluate. So here is about, we can focus on the binary variable 1, dv3, 1 and 3. Okay, so here you can focus on these two terms. Maybe this solution is not unique, so you can use another form to discuss this issue. Because this researcher is argue these two terms. So how about part 2 is about how about the test whether this researcher conjecture is better. So you should check the interaction term. Okay, so maybe I think I should add all regressor in a model column 7. Okay, so maybe I should add all regressor in column 7, because if you don't add all regressors, you cannot compare these two models. And part B is about the researcher is argued to the effect on the income and test score and small class. Okay, so income and class size. He argued the class size and income. So maybe you can use the interaction term between the income and the STR. So I use the income and STR interaction term to add plug into the model. And then you should evaluate whether this coefficient is significant. Okay, so I think that's all for the chapter 8. And next week I will talking about chapter 10. But in your homework 5, the programming part is about in chapter 11. So maybe I should make some schedule to talking about programming code for homework 5.